Same?
Yeah.
Okay, let me see. Okay, so here's what I've got. This was, let me see, let me go to here. This is what I have from last year on number 11. So I have 100 amps times 120 volts. So that's the, calculating the amount of watts you need. And then converting it from joules to kilojoules. Okay. And then I have, so that gives me watts, which is per second. So I get rid of the seconds and get to hours, and then I multiply by 24 hours a day and 365 days per year. And then I convert to, I use the enthalpy. So 2 times 10 to the 10th kilojoules per mole. So that gets me out of kilojoules and into moles. And then I get out of moles and into grams. So now I'm grams of uranium, but that's for perfect efficiency. And so then that's joules of thermal energy, right? And so then I got to go from thermal energy to from thermal energy. I don't know what's nuclear. Yeah, that's joules of nuclear. So I convert from joules of nuclear to joules of thermal energy, and then from thermal energy to mechanical energy, and then from mechanical energy to electrical energy. So that's how I got the 11 grams per year.
So I have multiplied by the efficiency, not divided by it. That's what I have done for
Interesting. Let me think about this. Oh yeah, so this was.
That's what I've done for number 3 is I multiplied by the efficiency.
Okay, so yeah, this right here, this is kilojoules. So let me show you why we're dividing by these things. Okay, so where's my pen? Let me make sure this is big. All right, so let's look at this. This is right here. This is kilojoule. This is joules electric. Right? Does that make sense? And so it's 98 joules. We're kind of working our way backwards. 98 joules of electric for every joule of mechanical energy. Let me just simplify this. So over here on this side, so this right here, this joules electric is on top. And this is kilojoules of nuclear, joules of nuclear on bottom. And so in taking into account the conversions, we need to take into account the mechanical to electrical conversion. So this joules of electric here cancels with this one, and we have joules of mechanical. And so then we take into account the thermal to mechanical conversion, and now we have joules of thermal, and then joules of thermal to nuclear, that's this 0.88. So dividing by these takes into account the needed efficiencies. So I find it helpful to use these little subscripts because everything's joules. And so if you use, that's the take-home lesson for this, is that use your subscripts. We did this in another, there was another set of problems where we had to keep track of our subscripts too, like make our own. I can't remember though. If you think about it, say something. Yeah, it might have been. Yeah. Yeah, because it was Kelvin and Kelvin.
So then it would be the 1.
No, that's a different problem.
Oh.
11 grams per year. So 11 grams is the answer that Blackboard's looking for. This is just showing you how you get there. Yeah. Did you get to the kilowatt hour thing?
Yeah.
Okay. And then you multiply by the number of hours and then the days of the year and so on, 24 hours a day. Get the top part, yeah.
I did not.
Yeah.
Okay. I didn't know what to do with what I had.
Yeah, and so that was just to recognize that you can't go straight from nuclear to electric without taking into account those efficiencies. So that's the deal. You're like, okay, well, it'd be nice if we could go straight from nuclear to electric, and you really, there's really no known way if we could figure that out, and if it could be more than like 30% efficient, then you would say you would make billions of dollars. So what is this efficiency? Let me see. 0.88 times 0.46 times 0.98. So that's 39. That's like the best I've ever seen. I mean, the U.S. grid is about 31% efficient. So this is like theoretically a little higher than that. But yeah, if you could get a transformation from nuclear straight to electricity, and it beat 39%, you've solved a lot of problems. Yeah. Especially if you could just take, think about the alpha particles that come out. They're charged. The beta particles, they're charged. The nuclei that come out, they're charged until they grab electrons. There's a lot of charges going on, but we have no way of capturing them at this point. So we're using it to detect them. Those charged particles come into our detectors, and we see a little tick, and you hear on the little detector. So that's the charged particles, but it doesn't generate a lot of electricity for us to use, but we're getting some kind of electrical effect. That's what we're using for detection. It'd be nice to be able to try to capture that. But a lot of the energy is in translation. So those alpha particles are coming out of there. There's a tiny little energy for the charge, but there's a lot of energy because it's going so fast. And so it comes into water and bangs around and delivers all that kinetic energy to water, and that heats it up. So that's where the heat comes from. And so then the heat of the water makes steam, and we spin a turbine. And so far, that's all we've been able to do with the nuclear furnace, is just to use the heat that it generates. It's still pretty low tech. It's just another heater. It's like burning natural gas or coal. We're just burning nuclear energy, burning nuclei. There's just so much more energy in the nucleus. Okay, what's next? It's interesting just to contrast this with 11 grams of uranium versus 36,000 grams, 36 kilograms of diesel. Yeah. But still, 81 pounds of diesel, that just doesn't seem, is that right? That's, that doesn't sound like enough. Oh, times 365 days a year. This is per day. Yeah, 29,000 pounds. So like 15 tons of diesel per year versus 11 grams of uranium.
I don't think it's more in class, but I think I forgot to factor in the efficiency.
I don't have them copied in here. I have the QSPR thing.
Oh, I did not get those.
Okay. So here's the QSPR equation, 32.1 plus 426 times the number of carbons plus 88 times the number of nitrogens. I guess the oxygen's not on there. Oh, it's just hydrogens. I'm sorry, 88 times the hydrogens. And then that gives you this so many kilojoules per mole. And then you divide by the molar mass, so you get kilojoules per gram. So that's our specific heat. This is the enthalpy of combustion. This is the specific heat of combustion. So joules per gram is specific. Anytime you hear the word specific, it's per gram or per mass. So that gets us 44 kilojoules per gram. So that's what this is.
Toss that out the window and then try calculating it with like the delta H.
From the tables?
Yeah.
Oh, yeah.
And then I got it wrong and then I was like,
yeah.
One more slide over.
That's right. And I know that the tables are more accurate because they're per compound, right? But you get like 98% correct answer or 95% correct answer with this one equation. No table needed, right? And so the table is better, but if you just have this simple equation, then you can calculate enthalpies of combustion right away, no matter what the substance. Well, CNOH, CNHO, CHNO. Yeah. So that's why I like that. I need to publish it. I had a student like write it up with me, and so it's like 90% done. I just haven't put it out there. Well, it's negotiable, I guess. I want to get them graded fast because I just am real busy at this time of year. And so I want to just do 50 questions of multiple choice, no written. And so then they're 2 points apiece. And so you can just, burn through it, turn it in. I can grade it. We're done. So that's what I'm leaning towards.
I like that.
You do? You'll have your grade by the end of the day, probably. Yeah. Probably both. It's a small group, yeah.
Oh, as far as like content, should I be looking at old exams or old homework?
Just look at the homeworks. I kind of go through and sort of look at them again, and then pull questions that are similar from all of those. Yeah. Yeah. Now I'm going to do that half Carnot cycle question. Give y'all another pass at it. Yeah.
Can we do that right now? I never understood any. Okay, that's a lie. Wait, I understood the Carnot cycle. I had that down.
The regular
but that test was not in my head a Carnot cycle, and so
it's half. Yeah.
Never understood it.
I saved you time.
No.
I think I would have done
With peace and love, but no.
Yeah, I'm telling you.
Yeah.
But I told you guys to work it,
I
did. But then you put 3 points on there instead of a full 4, and I don't know why that should be.
There were only 3, and it really
I know. But that's the thing. Then you didn't understand it. Yeah, you understand a procedure, right? But you got to not be procedural. Don't be procedural.
Are we going to get a level rule problem?
I can do the lever roll as long as there's.
Let's see, where's the Carnot cycle?
There's certain labeling.
Certain labeling? What do you mean?
Well, as long as everything's labeled how I think it should be based on how it is.
As long as I clearly understand every step. Yeah.
Yes.
As long as I know how to do the question, I'll know how to do the question.
Let me try to. Yeah, that's right. It's funny.
That was weird. Then I swapped my legs, and then everything was wrong, and I was like, I don't know what's going on.
Let me just try to find that one. Let's see, where is it?
I remember there was misidentifying each of the legs. And I was like, because I would forget what axes were actually given, and I would be like, yeah, it's obviously, I don't know, whatever I thought it was at the time. Then I looked at it again, I'm like, that is not what that says on directions, and I was like, Tommy, I'm not getting the right number. I don't know what's going on. He's like looking at it and looking at it, and then he realized that I swapped my legs.
Oh yeah, yeah, yeah.
You know, that'll do it.
Yeah, here the half Carnot.
Can you make a note card for nuclear fuel?
Yeah, for sure. You can make one more note card for the final. Keep all your other note cards. Let me turn on the display capture here. Yeah, so here we go. Here's the half Carnot. So this is your friend right here.
No, see this one. Okay. I'll tell you where to go. That seems backwards.
What's backwards? What do you mean?
A to B is not in the spot that I wanted it.
But A is the smallest volume.
Right.
C is the biggest volume.
Which is fine,
Mm-hmm.
but it was turned, and I didn't like that, and it threw me off. Then I
But what is A to B? What do you know about A to B?
no.
Like,
I
think of the
can't
terms. Think of
remember.
all the terms. Don't anybody say any of them. I'm going to quiz you.
Okay, so here are the things with the terms. The terms mean things to me, like isobar.
Yeah, okay.
Such.
Isocore,
Isocore.
isotherm,
Yeah, those
and
mean things to
adiabat
me.
doesn't have an iso in it, but it's an adiabat.
Right. So those mean. Yeah. So those mean things to
Yeah.
me.
Constant volume, which would be a vertical line on the volume scale. So you're looking at the volume scale. If it's vertical, isocore.
That's what I was looking for.
Horizontal is the same pressure all the way across, isobar.
So I was looking for A to B to be vertical because
A to B being what?
vertical.
Vertical?
Because that's just how I've always seen the Carnot cycle. So that's what that in my head that's how it should be. And it wasn't.
But no, here's the Carnot cycle. A to B is not vertical. This is A to B here.
Lies, this one. Boom. That's what I was looking for, and not.
Oh, that's the Otto cycle.
Oh, not that one.
Yeah,
Oh, wait. Okay. Oh, wait, A to B isn't vertical, but D to A is vertical.
but there's no D.
There's no D. So that's what threw me. So there wasn't a D, so that, like, automatically, I little bit them. Then
Let me go back to it, just so we have our
my
friend.
initial, like, there wasn't a D, and then everything from there just, like, fell apart. And then,
But that's the thing. I want you to like look at it and go, oh crap, what am I gonna do here? There's no D.
that's exactly what I did.
Right. So you've got to say,
didn't
you get this
past
is the
that.
thing that's got to happen. You got to go, okay, calm down.
I don't do that.
I know what an isobar is. I know what an isocore is. I know what an isotherm is. I know, and that's what I want. I want you to say, okay, what do I know? You find a spot and you're like, okay, I see that line goes straight across. I can't mark on Excel. That line goes straight across. You can see that it's a single pressure for every point on that line. So it has to be an isobar.
Right.
And so then I know how much work happens on an isobar. That's expansion against a constant pressure. So it's minus px times delta v.
Yeah.
So I know the work equation for that. Okay. And so then I might be able to use the ideal gas law to figure out what the temperatures are, because I know P and I know V, and maybe I can figure those things out. So that's why the state variables table is so important. You start working it with the ideal gas law and things given in the problem so that you can get your P points for all three spots and your T and your V. And so it's just one of those things. I want you to not panic, and I want you to like find a spot like a little beachhead and invade the problem. And like, okay, I'm going to go from this point on the state variables table to the next one. And then I'm going to look and say, okay, now I've got 3 of the 4 variables I can solve for the temperature. And then I've got, yeah.
Why I couldn't do that. Because I remember exactly why I couldn't do that. Something was missing, and I know nothing was missing because
Yeah.
apparently other people solved it.
No, they didn't.
Which
That's why I was so depressed.
No, I know.
I haven't solved math.
I
Good.
don't have.
Generally, I think if I had taken more time for it, I would have gotten it.
Yeah.
Fine.
I
Yeah.
I think the part that I was missing was I couldn't get the mold.
I couldn't get mold. I couldn't get
Because
the
I forgot
other
about the little
temperature.
conversion.
Something felt wrong.
I
So
had plugged in all the answers from the multiple choice and went, okay, which one of these works?
Real.
There you go. Yeah. And okay, so that may not be the way I want you to solve it, but it's a way, right? And if you can use your figure out skills,
Because I mean, if you're working
Yeah.
backwards, you still have to like know what equation.
but if that gets you to one of the like state variable table deals, and then it starts to kind of click and all fold in, you're like, okay, it's starting to be consistent. I did use, I think on that particular test, I set up, what do I want to say, red flag boundaries or something like that. When there's none of the above, you know you're off because none of the numbers are there. So it's like I'm here's the ski slope. I'm in the woods. Right? How do I get back to the slope? Right? I'm banging off the trees over here because there's no answers on any of the multiple choice, and I've got none of the aboves. Now that's frustrating, but that's actually a gift because you're like,
So
yeah. But it does allow you, if you run out of time, you're like, okay, best guess, right? I know this volume is bigger than that one, so it's eliminated half of them. I'm gonna got a 50-50 here, and I'm gonna go for it. Yeah. So,
All I know is you told me my Excel Carnot cycle was beautiful.
okay, great job on the chart.
No, because
I spent so much time making those colors perfect.
yeah, the project. Yeah, that's right.
So there was my point.
Okay.
I did not realize that steepness changed if it was adiabatic or
Oh, but
isothermic. I didn't understand. Like
that's in the notes. Like I beat that drum. I was on that. I was like, this is steeper than that.
This is steeper than that for sure. When there's 4, when there's 3,
But look, there's 2. There's only
But
2.
there's 4 points.
I
can
don't
look
care.
there,
There's only
because,
one
like,
80 in that option.
Yeah,
When
yeah,
there's
yeah.
4 points, I can look at B to A and be like, okay, that's steepness, and then C to D.
But man, it is
like,
so
that's
hard. Here's the
steepness.
Carnot cycle.
But
Okay, look at this.
I
Why can't I do
cannot
it?
visualize anything with that.
Okay, so
The leg is steeper.
okay, look at this. Look at this.
Definitely tells me, and I'm
I mean,
like,
it's hard to tell
And
because I'm not on PowerPoint. I can't use the pen. Okay, so this is hard to know if that green is steeper than this green, right? I mean, it's like, come on, that's so hard. Whereas this one, we've got 2 lines to compare, and the red is the red. If I'm on a bicycle, this is going to be faster than that one. Yeah.
do you have a question? Because there was something where I was still looking at it like a week ago, and I was like, I will never get this.
Yes, you will.
My thing is, I don't understand.
Never say never. It may not be this week. That's right. That's right. It used to be Mondays. Like we would have the PChem exam on Monday right
Why
after
did I know that's all
Thursday. In here.
Inorganic is 10-12.
Oh, maybe that's it.
But that's on Tuesday.
Oh,
I think it's Tuesday.
okay. Then I don't know what
The thing about this that I was confused on is I couldn't figure out which temperature I was supposed to use when I was calculating the work
Mm-hmm.
for the legs.
I need to see the problem. I can't remember because this is Excel. I can't remember what was given.
Oh, I have it.
But I've got the test here. Let me just pull it up. Oh my gosh, my mouse. I'm okay, let me see. Let me pull up the test. This is the thermodynamics.
Oh, 16 is really asking for the other temperature.
Is it the one after the CV?
Yeah.
That's the one I plugged in and I
what's crazy is I got my CV and I got those correct. I
Okay,
couldn't
so
get
this is
any of my volumes. And I think
okay. So let me try to do this. Where's my mouse?
where I had problems.
I'm gonna go in all my YouTube videos and I'm gonna clip all the times when I ask, "Where's my mouse?" I'm gonna do it like 500 times.
Well, I get extra credit if you do that.
Sure, I make a compilation video.
All my funny expressions. Yeah, that's right. So this is just okay. So it's proceeding in a clockwise manner because I got to tell you this is a new cycle. You have no idea, right? Okay. Here we go. Point C is at room temperature and 1 atmosphere. So that's.
I saw that statement and I still did not know how to get my it's like 16. Couldn't get it
16. We're 16.
during the test, and so everything came out right.
Yeah. So the adiabat is BC. So AC or CA is the isotherm. So A is at room temperature as well. So because you know that, and honestly, I really fiddled with the numbers so that this would line up on a tick mark. Yeah, so you're looking at the chart, and I promised you in class, I was like, look, the test graphs are going to be accurate to the problem. You know what I mean? Because sometimes people just throw a sketch up there of a Carnot cycle and give you all the numbers, but the graph is useless because it's a sketch, it's not an actual plot. So I wanted to provide an accurate plot so you could say, well, I know the volume is 1 liter, I know it's room temperature, so but where's the number of moles? How do we get the number of moles? Let me go over here to the Excel page and see. So C, I've got the pressure. Well, I've got the pressure and I've got the volume and I've got the temperature. So I just solve for the number of moles. So that's right away. You've got P, V, and T, so you need N. So you just solve for N. And then it's going to be the same N through the whole thing. So as soon as you solve for N, then notice these are equal to E16 because this E16 uses the P, V, and T values.
It's gonna look like that again.
Yeah, maybe not that same volume, temperature, and pressure. Yeah, it's a half Carnot. Yeah, because then you only have 3 legs to solve, and it breaks you out of the what we call the algorithmic model, where we teach you do this procedure, and we're never going to change it on you, and you're never going to have to really think. You just do the same thing over and over again.
But we're not gonna have like a 6 point.
No, because it's only. I mean, again, it's and it's going to be multiple choice, okay, and it is a 2-hour test, so I do have a little bit more freedom to give you a longer problem like this or lever rule, but as far as making it so ridiculously long you can't finish, I have no interest in that. Yeah. Don't take this the wrong way, but procedural thinking, where you just do what you've been trained to do and don't engage the brain, that is definitely like not bachelor level work. Because when you get out, you know, for companies that just run assembly lines and so on, they don't require a bachelor's degree. They can take people right out of high school, train them to do A through C, and the light comes on, I turn that knob, you know, I hook this clip in here. And I mean, I'm not downgrading that work. Those are great jobs, you know. But my goal is for no one in this room to ever be told, I don't pay you to think. Right? You don't want the job where you're not paid to think. You have a bachelor's degree in chemistry. Your level of work should be a place where you have to think, because the problems are going to present themselves in a slightly different manner, and I'm forcing you to do that. with a bit of pain, I admit.
Yeah.
But it's good because when you get out, you're like, oh, this is DW again. You know, you're at work and it's like, I know I can do this because I had to.
I think I wish I had thought ahead of time.
What?
I said I think I just wish I had thought ahead of time that I
Yeah.
may have possibly needed
To think through it. Yeah, I agree. No, it does sound way worse than it is, but it's, yeah.
Because it is so common that we do like constantly just like, this is what you do. Don't think any harder. Just use this over and over and over.
Don't feel bad. We built K through 12 that way because we want the students to be able to check enough boxes so we can say, look how good we're doing. You know, it's messy when you have to write problems for people to think because they're going to fail a lot. You learn more by messing up, but that doesn't look good on the standardized tests. So we've really we've harmed you guys by building this structure that way where you're procedural learners.
Can I ask
Yeah.
a question about certain assumptions I should or should not have made? Okay, on question 16, in the second exam, should I have made the assumption that the graph was accurate? Because that's the only way I would have gotten. 16?
Yeah. Okay, right down here.
16, because it's asking about temperature. And to use the temperature equation, it's the VB over VA. I didn't have those.
Those needed to be on your note card.
Oh, well, I mean, like, I didn't have those values. I have the equation.
Well, you have VB. Let's see, how do you have VB?
So that's what I was asking. Should I have made the assumption that the graph was like accurate? Okay, let me think about this. No, you can use the pressure at B. And you know the V and P of point C, and you know the P of B, and so you could find the V. I knew the P at B, but I didn't have
See
the
here,
N.
this right here is the equation.
So I think this is when I started feeling like something was missing.
Yeah. Okay. So the procedural way we did the Carnot cycle was we used. Did we use P and V relationships for that? We did. Okay. So it's the same adiabatic equation, but maybe a different variable that you're solving for. Okay. But we know the pressure at B. We know the pressure at C. So we have both pressures, and we know the V at C. So we're only missing one variable. We know it's water, so we know CV and CP. So we go gamma. We get gamma. So the only thing we don't have is that volume at B. So we can use the adiabatic relationship to get that volume.
Oh, I just used
graph. But with that,
yeah, you can, but I mean, I wanted you guys to use this relationship right here where my mouse is. Do you see that?
See, but to solve for VB,
you can't see that. Okay, over here. Where is it? Can you see my mouse now? Okay, yeah. This is what I wanted you to use.
Okay. Oh, no.
Because that is the adiabat from C to B.
Why would I do that? But you need the temperature.
So that's my problem.
You don't. You only need. Okay, well, once you get, I'm talking about filling out the state variables table, right? So I've got to find VB. That's the one that I don't know from that chart, right? I know. I'm trying to find this temperature right here. Okay, I guess I could have used P and T, these 4 points, and used the adiabatic relationship of pressure and temperature. You could do that. The reason the adiabatic relationships were derived is so that you only need a pair of variables. Okay, because all 3 variables are changing: pressure, temperature, and volume. But the adiabatic relationships with the gamma get rid of one of those. You've got 6 variables. It gets rid of 2 of them. And then you can use volume and temperature, volume and pressure, temperature and pressure. So if you change, again, you've got volume C, temperature C. We go up here and pressure C. And we go up here, we've got a new pressure that we can get right off the chart. And we can solve for that volume. Once we have that volume, we got pressure, volume, we can find temperature. If we did the temperature, once we get the temperature of that, we've got pressure and temperature, we could get volume. So it doesn't matter which one, you just need those two pairs and gamma, and you can get uphill or downhill, depending on which way you're going, using those adiabatic relationships. So that was the other thing. This problem had an adiabat, and I wanted you to use the adiabatic relationships. But in a pinch, you could use the chart. So you're looking at this, and you're like, man, that looks like about 1.45, not quite 1.5.
I was looking at it, I'm like, that
So-
looks like exactly 1.5.
So I said 1.45. I was off a little bit, but from the chart, it's 1.41. I mean, from the numbers, it's 1.41. From the chart, I said 1.45. So, yeah, it would have been close enough to probably get all of the multiple choices off the chart. But I don't like that because you didn't use the adiabatic relationship and the gamma, right? But it's okay, right?
Everything we had ever done up to that point for adiabatic involved the temperature. So I couldn't figure it out because I earned the delta T
Yeah.
specifically. And well,